Hello, good people. Welcome to this episode. In this video, I'm going to talk to you about activation functions. In some of the previous videos, I kept on talking about the fact that whenever you do your linear transformation, you run it through an activation function, which I also sometimes referred to as a threshold function. And this video is dedicated entirely to some of the most common activation functions that we use in the practice of deep learning. Now, this video is going to be a bit mathematical, but the objective here is not for you to be able to derive these activation functions. Neither are you supposed to be able to derive their first derivatives. Okay, the objective is to help you to develop an intuition as to why they work and when you use any of these activation functions out there. So let's get started. Now, I kept repeating in some of the videos that if you don't pass your data through an activation function, your neural network is essentially just doing a linear transformation of the data, because you always start off by multiplying your weight by the incoming data, you add a bias. So without any nonlinear function, without these first stage of the transformation going through any nonlinear function, you are basically just performing a linear transformation, and no matter how large or deep you make your neural network, you are still not going to be able to capture relationships between your data sets that are nonlinear. Now, I have already started off by importing NumPy, Matplotlib, and I also took this image of the internet, which is basically showing you the formulas for each of the activation functions out there and their derivatives. The reason why the derivatives are important, as you know from the previous video, is the way we do gradient descent is to calculate the partial derivative of the objective function with respect to each of the weights and the bias, and then we update them. That is how the neural network is able to learn up until the point where it converges. So I don't want to repeat myself in this video. Now, the first activation function we want to talk about is sigmoid. And the formula for the sigmoid activation is, if I ask you to calculate the sigmoid of x, it is essentially 1 divided by 1 plus the negative exponent. So exponent raised to the negative power of x. So let's go ahead and implement this in Python. Let me first of all insert a markdown cell, and then I will write sigmoid function. So for each function, we are going to plot the activation function and its corresponding derivative, and I will explain certain concepts to you. So let's implement the sigmoid. Sigmoid of x, sorry, I missed an I. Sigmoid of x is equal to 1 divided by 1 plus negative exponent of x. Okay, and the derivative, which I'm going to call sigmoid prime. I'm going to call this sigmoid prime. So the sigmoid prime of x is equal to sigmoid of x times 1 minus sigmoid of x. That is what you are seeing here. So it says the derivative of x of the sigmoid function is the sigmoid of x multiplied by 1 minus the sigmoid of x. At this point, if you know calculus, you definitely want to try out calculating the first derivative of the sigmoid function, as you can see here. But if you don't know calculus, do not worry about it. The good thing about deep learning is there are some formulas you might not understand now, and it's okay to use them, and you later get to understand them. There is always that aha moment when something clicks in your mind and you get to understand why things are the way they are. So I want you to trust research that has been done over years and has been proved to work for several use cases. And there is always the time in your career when you are going to get that aha moment and you understand why things work. So if you don't understand calculus, I don't want you to give up at this point. Okay, so we have defined these two functions, sigmoid and its first derivative. Let's go ahead and generate some data so that we will be able to plot. So I'm going to create data up here. I'll say np.arange. I want the numbers from -10 to 10 separated by 0.1. Okay, so let me run this cell. I'm going to run this, and I'm going to run this cell as well. All right, so now I'm going to plot a graph of the sigmoid and its derivative, and I'll explain to you how they work. Okay, so let's create a figure. Let's give it a size. I'm sorry. Let's give it a size of 15 by 18. So at this point, what I'm doing is just to prepare a plot. A plot that will show the sigmoid function and its derivative. And so I'm going to create two subplots on one row. So AX1. And by the way, if you don't understand Matplotlib, watch my playlist on Matplotlib. So I want one row, two columns, and then the first one. And then I'm going to say axis1.plot. I'm going to plot a sigmoid of data in the color blue. And I'm going to label it as sigmoid. Okay. And I'm going to plot the derivative of the same data set, that is the sigmoid prime. So what I can do is I'll just copy this line, paste it here, and I'm going to plot sigmoid prime of data. So as a matter of fact, I might not even need to do multiple plot here for simplicity, for those of you who do not know Matplotlib already. So I'm just going to plot them on the same graph. Let me change the color of the derivative to red. Okay. And let me also show the legend so that we know which is which. Great. So as you can see, the blue line represents the sigmoid function, and the red graph represents the derivative of the sigmoid function. What you are seeing here is the sigmoid function turns any of its input into an output which is within the range of 0 and 1. And it is true for all real numbers out there. Regardless of whatever number you feed into the sigmoid function, the output of it is going to be a number that is within the range of 0 and 1. Okay? And the way it captures nonlinear relationship is, as you can see from the plot, you can see that it is not a straight line. There are curves in there and it is smooth. I said in one of the videos that the most important prerequisite of every activation function is that it must be smooth and it must be a differentiable curve. And as you can see here, the blue curve is a smooth curve that is also differentiable, because we've been able to calculate the derivative of the sigmoid function here. Now, an interesting thing to note about the sigmoid function is, yes, it does translate every input into a number that is within the range of 0 and 1. However, you can see that for its derivative, there are regions where the gradient is almost 0. So you can see that in this region, the gradient is almost 0, and at this point the gradient is also almost zero. So the intuition you can build from this graph is that when you use the sigmoid function, there are certain range of input that will cause the derivative to be close to zero. And as you know from gradient descent, if the derivative is close to zero, then what it means is that your gradient descent algorithm is not going to keep updating the weight and the bias. Therefore, learning is going to halt or is going to be slow. So for this reason, most of the time we pre-process our data set to make sure that they are not too big. I mean, the scale of the numbers are not too wide. So we usually standardize our data set to be to have a mean of 0 and a standard deviation of 1. If this sounds too complex for you, don't worry. I'm going to have videos where I will explain everything. I just want you to see the different activation functions out there and their derivatives and form your own intuition, so that in later videos when I say something, you can always make a connection to this video and know why I am saying what I'm saying. So there are regions on the derivative where the gradient is almost 0, and so at this point the gradient is very small, and then the gradient descent algorithm is going to be slow, or the neural network will stop learning completely. And for this reason, we don't always use the sigmoid function as often as some other activation function which we'll be talking about. So this is it for the sigmoid function. Let's come up here and see for the tan h. So the tan h, which is also the hyperbolic tan, has this formula, which is 2 divided by 1 plus the negative 2x exponent minus 1. This is actually a simplification, but it looks more complex in this way. So I'm going to show you, I'm going to implement it in Python in another way. Okay, so let's come here and define our tan h. So tan h, the tan h of x, the tan h of x is actually, you return the exponent of x minus the exponent of negative x divided by the exponent of x plus the exponent of negative x. So this expression here is equivalent to the simplification, but then for writing the code I chose to write it in this way because it evaluates to the same value. If you do the simplification of exponent to the power x minus exponent to the power negative x divided by exponent to the power x plus exponent to the power negative x, it evaluates to the same value with this expression up here. Okay, with that done, let's go ahead and then define our tan h prime. So tan h prime, and that is going to be equal to 1 minus mp power tan h of x to the power 2. So as you can see from here, the derivative, the tan h derivative, the first derivative of the tan h function is equal to 1 minus the tan h of x squared. So that is what we have implemented in NumPy here. So 1 minus np dot power and then tan h of x to the power 2. So let's come down here and make a plot of tan h and its derivative on the same data. So I'm going to plot tan h, and then this is going to be tan h prime. Sorry, tan h prime. And let's see how the tan h function looks. So as you can see, the tan h function looks quite similar to the sigmoid activation function. But if you are observant, you realize that the range of the tan h function is actually from -1 to 1. So let's come here and see that of sigmoid. They almost have the same shape, and their derivatives also have a similar shape, but you can see that the range of the sigmoid function is from 0 to 1, and the range of the tan h function is from -1 to 1. And you can also see the derivative of the tan h activation function. Like the sigmoid function, we don't usually use tan h often, except in recurrent neural networks, which we'll be talking about in the future. And for sigmoid, we also don't use it in the hidden layers of a neural network. We usually use it at the last layer of a neural network, especially when we are performing logistic regression, which we will also talk about, or we are doing any binary classification task, because we want to fit the input data into two classes, either 0 or 1, and we want to predict probabilities of being in either of the classes. Don't worry if you don't understand this. I want you to build an intuition. I want you to be able to recognize the shape of these different activation functions when you see them, and I also want you to recognize the shape of their gradient, and the fact that because the gradient tends to be close to 0 or 0 in certain regions, there is a concept known as the diminishing gradient, where because your gradient is close to 0, learning slows down or halts completely. We call it diminishing gradient or vanishing gradient. These are all things that we'll be talking about. So the point here is not for you to be able to derive the formulas or the activations. I want you to see the graphs and then also see their derivatives, so that in future videos, when I mention sigmoid, tan, ReLU, and leaky ReLU, you know what I'm talking about. Okay, so let's move on to the ReLU activation function, which happens to be the commonest activation function that we use in deep learning, and I will explain to you the reason why it is so. So as you can see, the ReLU function takes in a value x, and then it returns 0 if x is less or equal to 0. Otherwise, it returns x. Okay, so it is more like taking the max between x and 0. So let's come here and implement the ReLU function. So def ReLU of x is going to return np dot where. So if x is greater than 0, then return x. Sorry, if x is greater than 0, then return 1. Otherwise, it is going to return, sorry. So if x is greater than 0, return x. Otherwise, return 0. Let's confirm that from the formula. So the formula says if x is less or equal to 0, you return 0. So if x is greater than 0, you return x. That is exactly what we have implemented down here. And then let's also implement the ReLU prime. So def ReLU prime of x is equal to return np.where x is greater than 0, return 1, otherwise 0. Okay, let's compare what we've written here to the formula in the image. So the derivative is 0 if x is less or equal to 0, and 1 if x is greater than 0. So let's see what we have implemented in Python. So if x is greater than 0, return 1, otherwise 0. All right, so let's go ahead and then plot the ReLU and its derivative, and I'll explain to you why it is the go-to activation function for most deep learning architectures. So let's plot ReLU and ReLU prime on the data. Okay, so what can we see here? What we can see is that the ReLU function almost looks linear. Okay, from this point up to this point, it looks like it's a linear activation function, and so you might think it's not possible to capture nonlinear relationships with it. What you are forgetting is that at this point onwards, it is not linear. Okay, so it is actually a nonlinear activation function. It looks linear for certain range of input, and for a certain range of input, you can see that it is not linear as you think. So this makes it a nonlinear activation function. And look at what is happening with the ReLU. So you can see that for the ReLU activation functions derivative, it is 1 look at the formula. It is 1 when the input is greater than 0, and it is 0 when the input is less or equal to 0. So as much as this also has the problem of the vanishing gradient, it is not as rampant as it is in the tan H and the sigmoid, because the tan H and the sigmoid has two regions where the gradient reduces to almost 0, and so it's going to really slow down the gradient descent algorithm, or it will stop it from learning anything at all. So we have two regions here for both tan H and sigmoid, but then for the ReLU activation function, you can see that there's only one region. So as long as you can keep your input into the function not to go into the range where the derivative is close to 0, then learning is going to keep happening at a good pace. Okay, so for this reason, the ReLU activation function is the commonest activation function used in most deep neural network architectures, and then we tend to use the tan H or the sigmoid as the activation functions for the output layers. We will talk about all these things so you understand them. Okay, we tend to use sigmoid and tan H for the output layers depending on what we want to predict at the end of the neural network. Now, the ReLU seems very sweet and good because it tends to in a way deal with the issue of vanishing gradient. However, it doesn't deal with it completely, because there is this half region where the gradient is completely 0. So if it happens that the data that is coming in at that layer of your neural network is always in the range where the derivative is 0, then it becomes hard for your neural network to learn anything. So for this reason, there is the leaky ReLU, which introduces another parameter known as the alpha, which ensures that your gradient is not 0 in the region where it is always 0 for the ReLU activation function. And the way it is handled is, look at the formula here. You can see that ReLU and leaky ReLU are very similar, with the exception of the introduction of another term known as the alpha. So you can see that the leaky ReLU of x is alpha times x if x is less or equal to 0, or x if x is greater than 0. And look at the gradient. You can see that there is no point in the gradient of the leaky ReLU where the gradient is completely 0. Because of the introduction of alpha, the gradient becomes a constant for that range in ReLU where they were otherwise 0. Okay, so let's go ahead and implement our leaky ReLU. And mind you, the alpha parameter is usually a small number like 0.01, 0.02. It is just introduced to make sure that this region of ReLU where the derivative is 0 stops being 0, so that learning can continue no matter which region your input falls in. Okay, so let's define our leaky ReLU. So def leaky ReLU, and then we're going to introduce our alpha parameter. By default, we're going to set it to 0.01, and then so it is going to return mp.where x is greater than 0, it has to return x. Otherwise, it has to return alpha times x. And let's define for leaky ReLU prime. So leaky ReLU prime of x. This is going to return mp.where. So I guess now you understand why it is important for you to spend some time to make sure you really understand NumPy. Otherwise, you will not enjoy anything going forward. Okay, so let's pass in our alpha here, which I'm also going to set to 0.01, sorry. So alpha is equal to 0.01. Okay, so it returns x when x is greater than 0, or it returns alpha times x, and the derivative returns 1 when x is greater than 0, or it returns alpha. So let's come here and make a plot of ReLU and leaky ReLU on the data. So let's plot leaky ReLU and leaky ReLU prime on our data set. So as you can see, look at the difference between the ReLU function and the leaky ReLU. You can see that the leaky ReLU function's derivative is not zero in this region. You can see that they do not overlap, as you can see over here, and it's all because of the introduction of our alpha. Let me try to bump up alpha a bit so that it makes it very clear in the graph. In practice, you don't set it this high. It is supposed to be a small number. Yes, so we just want you to see how the leaky ReLU is different from the ReLU over here. So you can see that there is no range where the leaky ReLU is exactly zero. At least in that range, it is going to give you something that is alpha, okay? And with the derivatives too is the same. From the graph, you cannot really tell that it is not exactly zero, but indeed it is returning alpha where ReLU would otherwise return zero. So I hope you've enjoyed this video up until this point. I know maybe because of the math, it might not sound as interesting as it's supposed to be, but like I said from the start, the objective here is not for you to be able to understand how they came about these formulas and how the derivatives are calculated. The good news is that most of the libraries we'll be using already implement automatic gradient calculations, also known as orthograd. So what we can do is, regardless of whatever activation function we use, those libraries are able to calculate their derivatives for us, and we don't need to worry about that. But that said, you also want to have an intuition. That is the biggest objective of this series. I want you to be able to at least have an intuition as to why things work the way they are. So now you have seen the various activation functions. In subsequent videos, when I talk of sigmoid, tanh, ReLU, leaky ReLU, and some other activation functions that you come across like the softmax, you will really understand because you have watched this video. And when I make mention of vanishing gradient, you also can picture in your mind why the gradient will be vanishing, because you have watched this video and you have seen how there are regions on the gradient for the various activation functions where the gradient is either zero or approaching zero, and in those regions the gradient descent algorithm will learn very slowly or might stop learning completely if the gradients are indeed zero. So thank you very much for watching. Don't forget to subscribe and leave your comments in the comment section below, and I'll see you in the next video.